Hello, I'm Dr. Mohit Kumar, currently working as a project scientist at IMD Pune. Today I'm going to present to you my work, which is titled Interseasonal Variation of Rainfall Microphysics as Observed over New Delhi, India. To introduce, we are measuring surface rainfall microphysics. Now, surface rainfall microphysics is closely related to cloud microphysics, as precipitation results from multi-scale interactions. And within clouds, raindrops undergo various microphysical processes. These cloud microphysical processes and hydrometeor content are reflected in the surface rainfall microphysics. Now, to understand the surface rainfall microphysics, RST, that is raindrop size distribution, is very crucial. And to measure the RST, we have used a Joss Belvogel distrometer. Our study area is located in India. It's a small region in India, which is Delhi, which is the capital of India. And this is the district map of Delhi. And we have applied the gamma distribution to the RST. Gamma distribution is a 3-parameter distribution, and this is the functional form of the gamma distribution. And we have to apply moments, and this is a general formula for moments. And given these moments and this functional form of gamma distribution, you can calculate the various parameters such as Tm in using some formulas. We have in order to analyze, we have also stratified rainfall based on two criteria. First is based on rain rate, and based on rain rate, we have stratified the raindrop spectra into 5 rain rate classes. These are the classes from 1 to 2, 2 to 5, 5 to 10, 10 to 20, and greater than 20 millimeter per hour rain rate. The rain rate classes were chosen in such a way that number of data points in each subseason is nearly identical for each class, as well as the mean rain rate of each class is nearly equal among 3 subseasons. This is the standard practice while choosing the rain rate classes. We have also stratified the raindrop spectra in convective versus stratiform. And to classify the spectra into stratiform or convective precipitation, we have used the methodology described by Chang et al. And that methodology is that if rain rate is greater than 10 millimeter per hour and the associated reflectivity is greater than 35 dBz and associated mean weighted mass diameter is greater than 1.9 mm, if all of these 3 conditions are met simultaneously, then only we say that it is convective. If any of the 3 conditions are not satisfied, then we say that it is stratiform. We have also used some satellite data, which is the GPM satellite data. We have obtained the IR brightness temperature from the GPM, and these readings, these IRBT readings, were averaged over the 3 years from the period from which we have used the data from the distrometer. So we have taken the distrometric data for 3 years, and we have also taken the IRBT data for those same 3 years. What we have calculated finally is that we have subtracted the brightness temperature obtained from GPM from the surface temperature, and we have defined it as differential temperature. So this differential temperature will prove useful later on in the analysis. Now coming on to the results, we have first thing that we have done is that we have tried to find out the seasonal variation in RST. So this is a typical RST plot, and we have also plotted some histograms of some rain integral parameters such as reflectivity, mu, lambda. We have also created a table of these values, mainly mean and standard deviation, skewness values. These are the histograms continued of rain integral parameters. And the main results that we have obtained from these is that in all the seasons, a majority of raindrops are mid-size over Delhi, and the dominant diameter range is 1.6 to 2 mm. The raindrops that fall over Delhi across the entire season, the majority of the raindrops fall within this diameter range. Also, rain rate is highest during monsoon, which tells us that most intense rain events over Delhi occur during the monsoon season, which is from June to September. Additionally, the monsoon season has highest concentration of small raindrops, and based on this, we have put up a hypothesis that given that small raindrops are highest in monsoon season, so we can assume that breakup process is most dominant during the monsoon season. The pre-monsoon season exhibits the highest DM, which tells us that the highest fraction of large drops in the spectra is seen during the pre-monsoon season. Also, a mu value of 5.96 suggests a broad RST. We have also calculated some standard mu lambda relations in all the three seasons over Delhi. As you can see, the functional form is slightly different in the three seasons. We have to calculate such mu lambda relations because they are very useful in retrieving RST parameters from polarimetric radar measurements. So they form a kind of link between distometer measurements and radar measurements. So that's they are useful. And in this table, actually, we have compared the mu lambda relations obtained by us and mu lambda relations that have been obtained in previous studies over India and also some other Asian places. The main result that we see in our relations is that both lambda and mu do not reach very high values in the post-M season, which shows that there is weak rain rate observed during this season, during the post-monsoon season. We have also calculated some ZR relations over all the three seasons, and as you can see, Z equal AR to the power B standard form. The coefficients are different and exponents are also different during the three seasons, and these relations are actually very important in the sense that there have been no previous attempts to decipher the Z relations over Delhi. So this is the first time that Z relations over Delhi has been obtained or find out. So main result is that exponent is greater than unity in all seasons, which shows that the dominant processes over Delhi throughout the year are the coalescence processes. Highest coefficient value during the pre-monsoon season again tell the same result, that highest fraction of large raindrops will be found during the pre-monsoon season over Delhi. Small coefficient values obtained from monsoon is due to the fact that although monsoon spectra also contains large drops, but it also contains small raindrops, high concentration of small raindrops as well. So that is the reason behind the smaller coefficient obtained for the monsoon season. Now after that, as told previously, that we had stratified the rain spectra into different rain rate classes. So we have also obtained the RST for those 5 classes. As you can see, we are getting the plots for all the 5 classes. And this is the table. Again, we have calculated some mean and standard deviation of basic rain integral parameters in all the 5 classes in all the 3 seasons. Now, some important results that come out of these tables and plots is that as rain rate increases, the distribution becomes broader, which tells that as rain rate becomes high, the drop size also become high, and large drops, that is diameter greater than 3 mm, start to appear beyond rain rate of 20 mm per hour. So over Delhi, you will not see large drops, that is drops with diameter greater than 3 mm in rain events which have a rain rate less than 20 mm per hour. We have also created a variation of DM and NW in different rain rate classes, and some very interesting results actually do come out of these plots. One of these is that observing the NW values in class C5, we observed that for pre-monsoon and post-monsoon, the NW values actually decrease while going from C4 to C5. This suggests that raindrops are colliding and coalescing as rain rate is increasing. But for the monsoon season, we actually see an opposite trend, that log NW values actually decrease while going from C4 to C5. This suggests that as the rain rate is increasing, new drops are getting generated through breakup processes. So this again tells that breakup process is important during the monsoon season. Observing the general pattern, pre-monsoon exhibits larger drops than monsoon within this window when the rain rate is less than 5 and greater than 20. But within this range, between 5 to 20, Actually, monsoon contains larger drops than pre-monsoon, and the NW is actually closely related to concentration of drops, and the NW values are increasing by going from C1 to C4, but there is a subsequent decrease in C5. This tells us an important result that contribution of drop size is more significant for the increase in rain rate than the number concentration over Delhi. After that, we have performed the stratification of convective and stratiform as well, and these are the plots that we have created. This is the typical RST plot. We have also constructed a DM NW plane for the convective and stratiform. We have created another table for the rain integral parameters, calculate the simple mean and standard deviation. Some very interesting results again come out of this stratification. First of this is that a clear distinction is evident between in convective rain exhibit higher concentration from large drops compared to stratiform rain. As we see here, the DM is higher for stratiform for convective compared to stratiform. Also in stratiform region, the pre-monsoon season exhibits the highest concentration drops across all diameter ranges. But in convective, monsoon season demonstrates the highest concentration in small and mid-size. So in stratiform region, actually pre-monsoon, you see the pre-monsoon rainfall is the most intense in stratiform region. But in convective region, the monsoon rainfall is most intense. During stratiform rain, the pre-monsoon season contains a higher proportion of large drops compared to monsoon, but during convective, monsoon exhibits higher percentage of large drops. So convective rainfall during monsoon is very intense, and stratiform rainfall during pre-monsoon is very intense over Delhi. An interesting observation is that DM for stratiform region in pre-monsoon is 1.49. As we can see here, DM here is 1.49. Compared to the other two, it is very high. So in the stratiform region, we are getting very large drops in the pre-monsoon season. This can be attributed to the aggregation of hydrometeors above the 0 degree Celsius isothermal level, because as you can see, during the pre-monsoon months, the surface temperature is very high, and this high surface temperature allows the stratiform clouds to reach great heights, and this allows aggregation of hydrometeors above the bright band, and this results in large drops during the stratiform rain during the pre-monsoon. Now again, the differential temperature that we had defined before, we have plotted the average differential temperature over the 3 years in all the 3 seasons. As you can see, the y-axis is percentage occurrence, and we can derive some important results from this plot of how the clouds are occurring in the 3 seasons over Delhi. And a higher differential temperature indicates greater vertical extent. So if the differential temperature is high, then we can safely say that the cloud has a great vertical extent. First thing to note is that significant occurrence of delta T greater than 25 Kelvin, that is above this range, higher this range, are observed only with the pre-monsoon here. Such values are absent in post-monsoon and occur only negligibly in monsoon. This indicates that's the most intense clouds with the greatest vertical extent. The tallest clouds over Delhi occur during the pre-monsoon season. However, over the monsoon months, a range of 7 to 25 Kelvin of delta T also suggests sufficient convective cloud fraction, and monsoon month is showing a significant occurrence percentage in this range. This shows that monsoon precipitation also contains a notable convective component. So during monsoon season, convective rain also occurs. A notable fraction occurs, and the shallow clouds, which is for delta T less than 7 Kelvin, the occurrence of shallow clouds is highest during the post-monsoon months over Delhi. So this is a very important result actually. Now we can derive several important conclusions from the study. First is that monsoon season has the highest number of rain samples and highest mean rain rate, followed by pre-monsoon. So consequently, the monsoon spectra shows the highest concentration of mid-size and large drops, while post-monsoon spectra exhibit the lowest concentration. The high variability in R values for monsoon season indicate that rain events during this period range from moderate to intense. So during the monsoon season, you will also see moderate rain events occurring, but you will also see intense rain events occurring. So the variability during the monsoon season is very high. We are observing high variability in that season. Similarly, the variability in DM values during the monsoon suggests a wide spectrum of raindrop sizes. That you will also find very small drops, but you will also find very large drops during the monsoon season. So there is high variability in rainfall during that season over Delhi. So the mu and lambda values are higher for the monsoon season compared to pre-monsoon season, which indicates that mid-size and small drops, fraction of them is higher during the monsoon compared to pre-monsoon. Pre-monsoon spectra contains mostly large drops, but monsoon spectra contains large drops but as well as small drops. Mu lambda relationship shows that lambda values increase the most in pre-monsoon season with increasing dew, again indicating a higher percentage of large drops. Analyzing the NW values in class C5, we note a decrease from C4 for PM and post-term, indicating raindrops are colliding and coalescing. But in monsoon, we see a decrease, which suggests that there are breakup processes also dominant during the monsoon season. The elevated levels of Cape water vapor surface temperature and surface winds, which were not shown here, but during the pre-monsoon and monsoon season, these parameters show very high values in contrast to post-monsoon. And that is why larger drops are significantly more prevalent during the former seasons. Because high surface winds, they evaporate the small drops, and so high surface temperature also evaporate the small drops. So you find more fraction of large drops during the pre-monsoon and monsoon. But during the post-monsoon, the wind is also low and the temperature is also low. So the small drops, they do not get evaporated, they are able to fall down to the surface. So we have found a larger fraction of small drops in the post-term rainfall spectrum. And again, when we notice the distribution of delta to differential temperature, that told us that convective clouds during the monsoon and pre-monsoon season over Delhi are prevalent. That a notable prevalence of convective clouds is there during pre-monsoon and pre-monsoon. But during the post-monsoon season, more than 70% of clouds, they are shallow clouds. So thank you. I end my presentation with this. Hope you are all doing well. Goodbye.